Hi everyone, welcome to solving inequalities using the number line method. This is Mrs. Casey here. We're going to go ahead and get started. Please make sure you always remember that if you need to, you stop the video so that you can copy things down. So before we actually jump right into the new topic, we are going to do a quick little review of how to write the equation of a polynomial from a graph. So our last video, we worked on just being given general information, and now we're going to look at it from a graph, but honestly, it is the same thing. You just now have to pick the information off of the graph. Hopefully, when you look at this one, you notice that this is, at the very least, a cubic function, but more so, it's an odd function, as is number 2. They are both odd functions. The powers will depend on what is happening at the zeros of each of the graphs. So for the first one here, you can see 3 zeros. You have a -5, a -2, and a +3. And it will be beneficial in this problem to also know that the y-intercept is -5. Each of these 3 zeros, all 3 of them, are cross-through points, which means the powers on each of them are odd. So when I go to write the polynomial and I write down the zeros, the powers on each of these will be at least to the first power. Since they are nice cross-throughs and they don't cross through like a cubic function, we can know that each of these points are just going to be to the first power. When I start writing this out, I'm going to write it like this: a times x plus 5, and again, this will be to the first, and then x plus 2 also to the first, and x minus 3 also to the first. Notice that this does create a cubic function. 3 first-degree zeros is going to give us a third-degree polynomial, but I haven't used the y-intercept yet. The most common mistake, which I think I mentioned before, is that most students want to just stick the y-intercept out here because you're used to the constant at the end of the problem being the y-intercept. But because this problem is already written in factored form, that will not give us the y-intercept. If you put 0 in for each of these things, you get 5 times 2, so ignore the a, right? You get 5 times 2 times -3, which is, when subtracted, from 5 doesn't give you 0. Okay, so that is not going to work. So goodbye. And instead, what we do is we now substitute the -5 in for y and the 0 in for x to solve for the leading coefficient that will create the correct shape of our graph. So when I do this, I get a is equal to, let's see here, what color, I can cancel out the 5s, I can cancel out the negatives, and now I'm dividing by 6, and so I get 1/6 is my leading coefficient. The final polynomial is x plus 5 times x plus 2 times x minus 3 with the 1/6 out front. No need whatsoever to distribute. Please don't do that. It'll actually make it harder on you and on me. You should have known from the very beginning that this was going to be a positive cubic function because the graph is going to -infinity on the left side and to positive infinity on the right side, which again, when we know our end behavior of our polynomials, we know that a cubic function, if it's a positive leading coefficient, is down on the left and up on the right. Okay, so the next one, I also have 3 zeros on this problem. The 2 of them are what I call bounce points or touch points. When we go to write the equation for this, again, I'm going to write a and out front for my leading coefficient. I have -3 is one of my zeros, and it's just a plain line cross through, so this is going to be to the first power. If I crossed it through that so that it looks kind of like a cubic function, then I would put this as to the third power. X equals 0 is just x, and then it becomes x squared because it's a bounce point. And then x minus 4 also is squared because it's a bounce point. So I have this polynomial, but I still need to get rid of the a out front. The problem here is that if I try and use the y-intercept, it's already the x-intercept as well, which then I just end up getting 0 equals 0, which is not very beneficial at all. So I instead have to find a different point on the graph. Usually I'll have one labeled for you. It looks like I forgot to do that on this problem, but we are going to use this one because I hope that you can tell it looks pretty spot on for being the point -1, 2. And if we can use a 1 or a -1 or a +1, that's going to make this a lot easier. So I'm going to put 2 in for y, -1 in for x, looks like I end up getting a is equal to 1 over 25. So then my equation is y equals 1 over 25. I'm going to put the x squared out front so it doesn't get lost. And there you have it. Hopefully that makes sense. We're going to go ahead and go on. The topic that we're talking about today is called the number line method. I should have labeled that at the top of the screen. The number line method is a way to solve both equations and inequalities, especially inequalities, without having to do a whole bunch of extra steps. It's more of a visual way to do it. You're not going to graph the whole thing, but you're also not going to solve the whole thing. It's kind of a best of both worlds. So I'm going to talk through each of the steps here. This is a worked out example on the left, and the steps are on the right. I would recommend writing the steps someplace on a piece of paper. So you start off with whatever the polynomial is and factor it as far as possible. Once you factor it, which, by the way, don't forget, when you factor it has to be equal to 0. Otherwise, this isn't going to work. Okay, so you have to have it equal to 0, just like a normal factoring problem. Once you've factored it, then you find the zeros and you put the zeros on the number line in the correct order. So on this problem, I factored it into 3x plus 1 times x plus 6, but x plus 6, that factor is -6. That needs to go on the left spot on the number line. Otherwise, you're going to get confused when you go to do the test. Step 3 is to test each region by selecting a number within the region, and you test that number in your original equation to determine if the value you get is positive or negative. So is the value you get above the x-axis or below the x-axis? So we have 3 regions in this case that we're checking. So we have this region to the right of -1/3, the region between -6 and -1/3, and to the left of -1/3. And you pick any value that fits into that region. The more often you can pick 0 or 1, the better you're going to be. But it does not matter, because no matter what you pick, everything in that region would have the same type of outcome. So I started off by picking 0 over to the right. You put 0 in, you get 1 times 6. It does not matter. Here's the 0 part right here. It does not matter if you actually solve it or not. You only need to know if it's positive or negative. So when I put 0 in for x, I get a positive number. 0 in here is another positive number, and a positive times a positive is a positive. The same thing applies then for each of the other regions. So if I put -2 in, you could also put -1 in. It doesn't matter. You put a negative in here, you get a negative for the whole entire parenthesis, and then put in the -1 or -2 in here. This is a positive. So a negative number times a positive number is a negative number. Same thing with this case, I chose -7. Huge negative, another negative, and a negative times a negative is a positive. Positive, negative, positive. Notice I labeled up here, positive, negative, positive. Let me actually get rid of some of this stuff here. So now you're looking back at the problem. Honestly, at this point, it doesn't even matter if you have looked to see if there's a less than or equal to sign. It only matters after you do all of the positive, negative stuff. The original problem had this less than sign, so less than 0. Less than 0 is negative values. So that means that this is the only window of values that are less than 0. And then since it has a less than or equal to sign, then that means notice I put these closed circles at -6 and -1/3. And when you write the answer, it's -6 to -1/3 with the brackets. So these points are included because it is greater than or equal to, not greater than, less than or equal to, less than. Okay? That is how the number line method works. We're going to do a couple of more examples that hopefully as we go slowly, if you didn't get this process, you'll start to get it. This is on your handout. So instead of it being a function that's already written for you, it's a graph that's already written for you. This is to help you see how the number line works, okay? It says use the graph of f of x for which f of x is greater than 0. We want to solve this. When is f of x greater than 0? And this is f of x right here. Hopefully you can tell by looking at the graph that occurs here and here, okay? So that means that the solution to this question is, well, from -infinity all the way to x equals 0, I have a graph that's above the x-axis. Then there's some stuff below. Then I hit 4, and from 4 to infinity, it's above the x-axis again. I don't have brackets because this is just a greater than only sign. All right, so now we're going to write the equation so that I can use the method that I just described to you on the previous slide to do that down here as well. Okay, so the good news about this is a really easy problem to write, but it is best if you write it in its factored form as opposed to in its standard form. One of the zeros is 0, so I get x here. The other 0 is 4, so I get x minus 4 in this spot here. Remember what we're trying to solve is when is this function, when is x times x minus 4 greater than 0? So this is the inequality that we're now going to solve with that number line method. The number line method, remember, is draw your number line, and you put the 2 zeros, or 3 or 4 or 5 or however many zeros on the x-axis. So they are 0 and 4. These are going to be good old open circles because it's just greater than. And then we test. When we test, we're going to test between 4 and infinity, or to the right of 4, between 0 and 4, and from -infinity to 0. Pick any value you want. I'm going to pick 5, let's say. So if I put 5 in for x, I get 5 times 1 is a positive number. Now I'm going to pick something between 0 and 4. So if I put 1 in for x, I get a positive times a negative, which is a negative value. Then I'm going to pick something to the left of 0, like -1. And I get a negative times a negative, which happens to be a positive. And remember that our problem is greater than, so I want all positive values. So that means this would be my number line solution, which if you look back at our original graph, basically what I could do on my number line even is I could even draw a little sketch of my parabola that fits right over the number line that I created. And then I can write this out in interval notation, which we already did above. But now that we've done it with the number line method, I'm hoping that you'll see it that way as well. All right, moving on. Okay, so normally if we were in class, we would do this together a little bit more slowly. I'm going to go through it pretty fast. I hope that I don't go through it too fast for you. But again, remember, please pause, send us questions, put questions in the question document for us to help you out. This question is saying use the graph to determine the values of x for which the function f of x, which is this, is less than 0. So I've already highlighted where it is less than 0 in there. So now I just have to write that out. But I'm not going to actually write it here. I'm going to write it down in this interval spot when I get down there. I'm going to go ahead and write out this function. So this function will be x plus 2 times x minus 1. It's a parabola, so both of those zeros have first degree powers. I want it to be less than 0, so this would be the inequality written out in this format. Number line method tells me to put the zeros on a number line. I'm going to put open circles because it is a less than sign and not less than or equal to. And I am going to test values within each of the 3 regions that we created. Okay, so test to the right of 1, like 2. Put a 2 in for x, I get a positive times a positive, which is a positive. Put something in between negative 2 and 1, like 0, and I get a positive times a negative, which is a negative. And then to the left of negative 2, like negative 3, would be a negative times a negative, which is a positive. And again, since I want less than, now this is the region that I am looking to solve for, or that I'm looking at. Here is my little graph. It goes just like this. And now I know that my interval notational answer will be negative 2 to 1. Moving on. We are going to, I think, skip number 1. Well, let's just go ahead and do it. I'm trying to make sure we get through as much as we can and don't make this video too long. But so this question says, on what interval is the line greater than the polynomial? It's really just a trick question to make sure you're paying attention. So the line is greater than the polynomial. It looks like from negative infinity to this number here. Well, it's great that the graph doesn't tell you what the x values are. This is the y-axis here. This is the line 10, but this is 1, 2, 3, 4. So from negative infinity to 4, and then from 4 to 4, 5, 6. It's the greater than thing that makes you have to write it like that. If that's a greater than or equal to, then you could just go from negative infinity to 6. Okay, so now we're going to do this problem here, but the difficulty with this problem is that it is not with a 0 on the right-hand side. So you can't use the number line method when it's written in this format. Instead, you have to square it, FOIL it. So we've got x squared plus 2x minus 4x minus 8 greater than 7. X squared minus 2x minus 15 greater than 0. Now we can use the number line method. Otherwise, you'd have to graph this polynomial, graph this quadratic, graph the line y equals 7, and find the intersection, which if you have a calculator, that'd be great, but these will be non-calculator questions. Okay, this factors into x minus 5 times x plus 3. So for our number line method, we put the negative 3 first and the positive 5 second. Open circles because this is just greater than and not greater than or equal to. And we test. To the right of 5, like a 6, I get a positive times a positive, which is a positive. Between negative 3 and 5, like 0, will give me a negative times a positive, which is a negative. And to the left of negative 3, like a negative 4, would be a negative times a negative, which is a positive. This problem is asking me for greater than, so that means I want everything that is positive. So my final solution will be negative infinity to negative 3 and 5 to infinity. All right, here we go. Now we're getting to the fun ones here. So now I have two problems that are not parabolas any longer, but in this, like number three's case, it's a fourth degree polynomial, and we have a bounce point on top of it. So we've got a couple of different things going on. But the good news on this one is that it's already factored and already has 0 on the other side. So we don't have to do a whole lot of work besides draw our number line. Again, remember the numbers have to go in order from left to right. So my first one is a -3, then a +1, then a +5. It is less than or equal to, so I'm going to put closed circles on everything. Although it's not looking like that with my stylus here. And now we test. So let's see, to the right of 5, I'm going to put a positive, like a 6. Okay, so positive times a positive times a positive is a positive. Between 1 and 5, no matter what we put in here, it's going to be positive. But let's say I'm putting a 2 in, it doesn't matter, it's still positive. Put a 2 in here, positive. Put a 2 in here, positive. Positive times a positive times a positive is a positive. Now I'm going to put something in between -3 and 1, like a 0. Again, whatever I put here is still positive. So I have a positive times a negative times a positive. So positive times a negative is a negative. A negative times a positive is a negative again. And then to the left of -3, like -4, will give me a positive times a negative, which is a negative, times another negative, which is a positive. We only have this little tiny window for our answers, -3 to 1. And if you want to think about graphing this, this is a fourth degree polynomial that is opening up on the left, up on the right. -3 is a cross through point, so we'll go cross through. +1 is a cross through. +5 is a bounce point, and it goes back up. So I've got positive, positive, oh, there's that negative we were talking about, and then positive again. All right, last problem I'm going to do with you here. So we have this x cubed plus 8. It has to be factored. I'm going to tell you that page 962 in your book has the formulas for factoring cubics. Please look at it, memorize it if you haven't already done so, because all the way through calculus, it's still going to come back to haunt you if you don't remember how to do it. Same, opposite, plus is probably something that you learned in one of your previous classes. This quadratic, whenever you factor a sum or a difference of two cubes, you get this quadratic, is never factorable, and it is always all positive, meaning it's always above the x-axis. So you only have 1 0 at -2, and you're just testing on either side. So if I put like a -3 in here, I put a -3 in here, I get a negative times this whole part's going to be positive, so a negative times a positive is a negative. And then if I put something like 0 on the right-hand side over here, so positive here, this is still a positive here, so the whole thing is positive. So you have a negative on the left, positive on the right. I want all the negative values. That's over there. -infinity to -2. This cubic function it's a cubic. Leading coefficient is positive. Starts down on the left, crosses through, and then goes up on the right. Okay. I hope that makes some sense. Again, remember to put questions that you might have in the question and answer document.